Let's begin this lesson with a puzzle. I want to assume that we have a triangle that looks something like this, all right? And we're given a little bit of information. Let's say we've been given the distance from A to C as being 6 units. Let's call it, for lack of anything better, 6 kilometers long. A big, huge triangle, 6 kilometers long. Further, we've been also been given the distance BC. And let's say that that's 9 kilometers, okay? And what else information can we have here? Let us lastly say that we've been given this angle, ACB, or angle C. And let's say we've been told that it is 49 degrees. Okay. Now, we're not given much information here, but I'm going to show you a way now that we can actually suss out and solve the entire triangle, all of the missing angles and the last missing side. And to do that, I'm going to have to erase what I started there. So I'm just going to recreate the triangle as best I can here. We'll call that C, B, and A. And that's 6 units, that's 9 units, and there is 49 degrees, okay? You can't use any of the trigonometry that you currently know because none of those angles look like any of those special angles. I mean, you know how to deal with angles that are, 60 degrees and 45 degrees and 30 degrees, and even 15 degrees, right? If you look at, say, 60 minus 45 and so forth. But 49 degrees, that's a weird one all by itself. You can't use Pythagoras much because, well, this isn't a right angle triangle. You might want to assume that a right there is a right angle triangle. It kind of looks right angle-ish, but you cannot make that presumption. So I'm going to walk you through something called the cosine law. And we're going to derive it together and show you how using some basic trigonometric tools that you already have in your toolbox and a little dose of Pythagoras that we can actually solve this triangle. We are going to start by labeling some stuff and then adding some lines to make this diagram a little bit more complicated. But we're going to start by labeling the sides, okay? And you know that opposite sides triangles are labeled by the little letters of the opposite angles. So C and B are over there, and A looks to be the hypotenuse on the bottom there. The next thing I'm going to do is draw a vertical from angle A. I'm going to bring it straight down, and I'm telling you that that's a right angle triangle, okay? I guess to move this conversation along a little bit, we should label this intersection where A comes down to the bottom, the base of CB. Let's call it D because we have an open letter, okay? That's capital D. And that might not look like an angle, but of course it is, right? It's a flat angle of 180 degrees, two 90-degree angles. So let's go ahead and label some new sides now. All right. So this height AD, we're going to call that H. Okay, that makes sense. It's the height of the overall triangle. But now we've got H as a labeled side of triangle ADB. And then why don't I go left to right? I'm going to label this distance from C to D as being X. And then I think if I label that as X, you can see quite clearly that this side DB must be A minus X, okay? Because remember, A is this length here, okay? And so DB has got to be that overall length minus whatever X is, okay? Erasing just to unclutter. And now I think we have enough information to help derive some kind of series of relationships that'll help us solve for that missing side C, because that's really what we're looking for in that triangle. All right, so what's the first step? Let's look at triangle ABD, okay? ABD. That's this triangle right here. For triangle ABD, we know that C squared equals H squared plus, well, not A squared, but A minus X quantity squared, okay? There's some basic Pythagoras for you, all right? And if we expand this a little bit, we can get H squared plus, looks like A squared plus X squared minus 2AX, okay? I've just expanded that easy polynomial and given us those expanded terms. Let's take a look now at triangle ACD, that one there. All right. So for triangle ACD, which is different than ABD, which is different than ABD, we can build up a Pythagorean relationship as well. We can say here that b squared equals h squared plus x squared. Right? It's a little bit of a simpler side here, isn't it? It's just x, not a minus x. But we can do one more thing with triangle ACD. And I'm going to do on ACD because I've got all sorts of single letters there, which makes it easy to simplify later on. I'm going to take the cosine of C. Now, what is cosine of C? Cosine of C is adjacent over hypotenuse. So that's just going to be x over b, just like that. All right? Just like that. I think we have enough information here to maybe combine a few formulas and see if something simpler doesn't pop out at 10. And by simple, I mean something with maybe one or two fewer unknown values, A's, B's, X's, H's, whatever. But by simpler, I really mean something that you can actually use to solve this. All right. So what I'd like you to make note of is take a look that we have an h squared and an h squared in those two formulas. In fact, we have an x squared and an x squared. And in fact, not only that, but if I rearrange this formula here and just isolate that, all I've done is rearrange this formula to go to here. I'm just rearranging some terms. You may have noticed that now I've got a representation for h squared plus x squared that I could sub in there. And when I do substitute it in, I'm going to get c squared equals a squared plus b squared, right? Because h squared plus x squared is being replaced by b squared minus 2ax. All right. Now, that looks, well, doesn't look much simpler, does it? So we're going to go over to what I did in Lilac over here, and we're going to see if we can't use some information there. Notice that if we could get rid of this x, then we could have this whole expression here expressed in terms of a's and b's and stuff, right? So why don't I go back to cos C equals x over b and just rearrange it in terms of x. X, using some very, very simple trig, is going to be b cos capital C, b cos C. And now you'll see what I've got going on here. This whole bit can replace the x. Now, it's going to make the formula a little bit more complicated, but it's going to make it simpler in a sense that I'm going to have fewer unknowns. So what am I going to do when I sub b cos C for x over here? I'm going to get c squared equals a squared plus b squared minus 2ab cos C. And now I have my entire formula expressed in terms of a's and b's and some trig function of angle C. In other words, to solve for C, I need this, I need that, and I need to know what theta is, what that angle C is. And if you go look, there's side B, there's side A, and I have a theta of 49 degrees. It looks like I might be able to solve for side C. So let's go ahead and do that. So what formula are we working with here? Well, we're working with this one here. We worked out the derivation that c squared equals a squared plus b squared minus 2ab cos C. And if I take the square root of both sides, then c is simply going to be equal to the positive square root. The negative will be an extraneous root for this question. A squared plus b squared minus 2ab cos C. Okay. And so let's throw some numbers in. A equals 9, B equals 6, and angle C equals 49 degrees. We should be able to get this to work for us. Okay. Well, C equals the square root of a squared. So 6 squared plus 9 squared minus 2 times 6 times 9 times cosine of 49 degrees. And if I do some simplifying, well, I'm going to use the magic of my calculator to say that this will be the square root of about 46.1456 or so, which will equal to, when I take the square root, 6 point, well, let's round it to a tenth, 6.8 units. And there we go. And thus, using some very, very simple trigonometry and the help of a little bit of Pythagoras, we can figure out a missing side length. So what does this all mean? Let's go take a look at the notes here. When solving for right triangles, and this was not a right triangle, but let's step back. For when we're trying to solve right triangles, we can use either the Pythagorean relationship when we know two of the side lengths, or we can use the primary trig ratios when we know one side and one angle. But we cannot use these tools when solving for not right triangles. Now, non-right triangles like this one, ABC, they're called oblique. They have a name. They're called oblique triangles. And we can't use the primary trig ratios or Pythagoras to solve these alone. We have to use something called the cosine law, which tells us that a squared plus b squared minus 2ab times the cosine of angle C, side, angle, side. All right. Well, let's try to apply this a little bit more now. Let's see if we can be useful. Moving on to page 251. Two planes left an airport and are flying off in different directions. The angle between their flight paths is 47 degrees. 1 hour later, plane A has traveled 850, and plane B has traveled 900. How far apart are they at the end? Okay, so what we got here is an airport. And one plane zooms off in this direction, and it's gone 900 kilometers. And another one has gone off in this direction here, and it's gone 850 kilometers. And what we want to do is figure out this distance here. Let's call it x, okay? And the last little bit of information we have is that the angle between the flight paths is 47 degrees, 47 degrees. Information here, we know that side B is 850 kilometers. We know that side A is 900 kilometers, and we know that theta is 47 degrees. And furthermore, you have remembered that that unknown side is going to be equal to the square root of a squared plus b squared minus 2ab times cosine theta. Now, don't be thrown here by the lettering and by the labeling, okay? We happen to have plane A and plane B, but instead of the length or the distance, C, we're calling it X, okay? And instead of angle C, we're calling it theta. Don't be confused by that. Also, don't be confused that I've given you that opposite side, side X, as being the square root of all that mess, right? Because it's really C squared equals a squared plus b squared dot 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 and all that stuff. So I'm just taking the square root of both sides, okay? Don't get confused by that. You're in grade 11. You can handle this. When I do some math here, well, I mean, I'm going to get 900 squared plus 850 squared minus 2 times 850 times 900. Okay, I've confused A and B. I've flipped them again. Cosine 47 degrees, okay? And when you go ahead and clunk that into your calculator, I think you get the square root of 489,042.509, carry the 4, 1. Okay, good. All right. And what this means really is that we get x equals, I think, 699.3 kilometers. Okay. And that's how you use the cosine law. All right, let's continue. The biggest difficulty when dealing with word problems is trying to figure out what's happening. And the best way to do that is with a diagram or a sketch. Always, always, always. So if we have two cruises leaving the same port at the same time, we've got a cruise A that's going northwest, 55 degrees. Okay, we've got to figure out how to do that. And it's going south by west, 63 degrees. So we have to figure out how to do that. 37 kilometers per hour. How far are the two ships apart 3 hours later? I'm going to erase this, but just very quickly here, if this is the port and one ship is traveling north by west, that's going to be in this direction somewhere. And the other ship is traveling south by west, that's in this direction, right? Because north, south, east, west, okay? We know we're going to work in quadrants. Looks like quadrant 2 and quadrant 3 are where the ships. And so wherever these end up there. So north, 55 degrees west. What that means is from the northerly direction, we're going to rotate 55 degrees that way. And so this angle here is going to be 55 degrees, okay? That's what north 55 west means. South 63 degrees west. means starting in the southerly direction, we're going to be moving this way. And so we're creating that angle there, and that angle is 63 degrees. And now if we realize that this angle here is going to be equal to 180, which is this, minus 55 minus 63, or 62 degrees, then I think we have a little bit more information here. So let's draw this situation out properly. Then I'll erase this mess, and then we can go ahead and solve it. So there's the port. There goes one ship, and there goes the other ship. And we know that this interior angle here is 62 degrees because we figured it out from there. And we know some distances as well. What distances do we know? Well, this is the first ship, 30 kilometers per hour. And so after 3 hours, this distance here is 90 kilometers. And this ship here, going at 37 kilometers an hour, it will have gone a little bit further. 37 times 3, or 111 kilometers. And now I think we have enough information to figure out this distance here, how far apart the two cruise ships are. Okay, and let's just call that x. And let us now, because we went from this diagram to that diagram, let's just erase all this so we have a little bit of room to solve. All right, cosine law. Cosine law says that side C, the opposite side of the angle, in our case it's x, is equal to the square root of a squared plus b squared minus 2ab cosine theta. Okay? Now you might not see that in your formula page, but you'll know how to interpret it. You see it in your formula page as c squared equals a squared plus b squared, yada, 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 okay? I'm just changing it around a little bit to represent the information that we got. All right, so 90 squared plus 111 squared minus 2 times 90 times 111 times cosine 62. When we simplify it, well, you can go ahead and do it. I'm going to get x equals 105.1 kilometer. And this is with the reminder because, you know, when you take the square root of a number, you get a plus or minus, right? We're only interested in values that are greater than 0. The other ones, any negative values, will be extraneous roots to the solution. So the answer is 105.1 kilometers. Boom, we are done. All right, let's see if we can do a bit of review, and I think we have one more sample question to do here. We're going down to page 253. We can use the cosine law to determine an angle if we know all three sides of a triangle too, if we know side, side, side. Look at that. Because so far we've been dealing with side, angle, side, but now I'm going to show you how we can use the cosine law to solve a side, side, side issue. Side, side, side kind of triangle. No angles, just the side lengths. We start with c squared equals a squared plus b squared minus 2ab cosine c. Wow, that's right there, right? Okay, so we're going to start with that. And what we're going to do now is isolate for cos c. And to isolate for cos c, I really need to get rid of that coefficient in front of cos c. So I'm going to divide the whole mess by 2ab, all right? And then that's going to give me something that looks like, to begin with, it's going to look like c squared over 2ab equals a squared plus b squared over 2ab minus cos c. That's what it's first going to look like. And then when I bring cos c all by itself by subtracting cos c from both sides, I'm going to get cos c equals, looks like a squared plus b squared. Remember, this is going to the other side of the equal sign. I've got to bring that over, so it's going to be minus c squared. And because the denominators are both the same, I simply write 2ab, just like that. And there is the second derivation, or the second version of the cosine law that you will see and be expected to use now to problem solve, all laying out for you. So let's see how we apply this to a real life math problem like this, where we're given side, side, side. This is an SSS triangle, side, 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 okay? And we're going to start, and I always encourage you to start by writing down the formula. Go look at your formula page because we will give you both forms of the cosine law. You do not have to remember that cos C equals a squared plus b squared minus c squared all over 2ab. You don't have to remember that, but you should write it out, and you should remind yourself that A is going to be 15, B is going to be 8, and C finally is going to be 11. And so all we got to do is plop those numbers in there and try to figure stuff out. So let's do that. And so let's start with cos C equals 15 squared plus 8 squared minus 11 squared, like that, all over 2 times 15 times 8. And if we start simplifying this, let me do two simplifications. Let me solve for C now as opposed to cos C. I'm not interested in cosine C. I want to know what the angle is. So C is going to be the arc cos, or cos inverse 1, or the inverse cosine of, well, on the top I'm going to have, I think, 168, and on the bottom I will have 240. And when I do arc cos of that, I'm going to get 45.57299, so 45.6 degrees. There is my angle, and that is what is being asked. All done. Bravo! We are about done. So here's a question for you. Do you think that the cosine law would work on right angle triangles? Why or why not? Why don't you try one? You know some basic triangles. You know, for example, that there's a 3, 4, 5 triangle, which is one of the Pythagorean triplets. Why don't you try the cosine law on this and see if it works for you? But if you don't have a right angle triangle, we've seen how we can use this cosine law in its two derivations. If you know a side, an angle, and a side, with that angle being in between the angle formed by those two sides, or you know three sides, then you can use the cosine law. Go forth and plunder this math. Use what you know about cosine law, and happy mathing.